Okay, so I think we can start. So as an organizer of this PhD program, I'm very honored and happy to present to the speaker of this course, Theodore'a Slaman, professor of mathematics in the University of Berkeley, one of the world center of logic, actually somehow related to historically to Alfred Tarski. Well, Theodore, he worked in recursion theory and Turing degrees, and so it's mathematics, but quite relevant for computer science as well. So we will have this lecture on computability theory from the perspective of set theory and measure theory.
Thank you. Okay, thank you for the opportunity to speak and for.
Sorry.
1 minute.
During the break, yes, there will be downstairs as usual. There will be some biscuits and coffee. Yes, informal cook. She's just one stir. I'm sorry.
It's okay. Thanks. Okay. Okay, so welcome everybody. Thanks for coming and thank you for the kind invitation. I wasn't quite sure what topics to cover in these lectures, so I decided to include topics from several different sources and try to frame the discussion of those topics from a single perspective, which is the perspective that one takes when you want to analyze a mathematical situation in terms of how that situation is represented. And so the perspective is going to be, let's see, a computability or a definability perspective. And the topic that I want to apply that perspective to is the topic of measure and randomness. So measure typically applies in familiar context to a subset of the reals or a subset of the plane, a subset of Rn. So you talk about the size of a set, and then randomness usually talks about an element. And so if you choose a point at random, right, choose a real number at random, right, you are, that phrase means you want to find a typical element of a set, and the typicality is in terms of how you've ascribed size to the set. Okay, so we're going to talk about those dual notions. So the Lebesgue measure of a set of reals is an indication of the size of the set, and you could think of it as the integral of the characteristic function of the set. Okay, now there are a lot of different measures that one can put on the reals, and so the Lebesgue measure is the one that assigns the same size to any two intervals of equal length. Okay, Hausdorff dimension of a set is a numerical indication of, you could sort of say, the geometric fullness of the set, how thick the set is. And Hausdorff dimension is a tool to distinguish between sets that all are measure zero in the sense of Lebesgue. Okay. So Hausdorff dimension, you could say, is a generalization of Lebesgue measure. Sets of positive measure all have, this is as a subset of the line, a set of positive measure has dimension 1. So measure is sort of distinguishing between sets that have full dimension and sets that do not. Right? Hausdorff dimension gives you some number between 0 and 1, if we're talking about subsets of the line. Okay, now, if you take this point of view of analyzing things in terms of the complexity of their specifications, right, then you get into what's called the effective theory. So effective randomness, effective Hausdorff dimension, those are variants on the classical notions in which the descriptive content, right, is taken into account. Okay, so we want to talk about the connections between viewing things as random with regard to certain criteria. Those criteria are measured in terms of how difficult it is to define things, and their classical notions. Okay. So what's the perspective that we're going to follow? Well, this is the computability theoretic perspective. So if you're thinking about things from the point of view of logic and language and so on, the thing that you're analyzing is the relationship between the user of math, who's trying to understand some mathematical situation, right, and the objects themselves. And sometimes the representations have to be analyzed in conjunction with trying to understand the mathematical situation that they are describing. Okay, so I'm going to give some examples that are sort of logically motivated and some examples that go back 150 years, which are kind of number theoretically motivated or geometrically motivated. Okay, so when you want to understand this descriptive complexity of mathematical objects, well then there's a whole subject that's associated with doing that. Computability theory, it's in that subject, one develops methods to directly understand the complexity of descriptions, build objects that can be described in this way and not that way, give a kind of fine structure to how this interaction between describing something and figuring out what's true about it. Okay. And this minimalism is where you have a certain kind of methodology to build something, and then you'd like to find out what's the generic object, what is the unencumbered object that can be described this way. Okay, with no special tricks or features. Okay, this kind of point of view of computability theory, it's a different branch of math. It gives you a way of thinking, right? Just like one can approach mathematical problems algebraically or geometrically or analytically, right? It's a way of organizing your thoughts. Some parts of a mathematical subject are put in the background and others come to the foreground. You know, just like when you apply any other kind of mathematical technology. If you're thinking about things algebraically and doing a lot of symbolic manipulation, it's a lot different than doing analysis, where there's typically a lot of estimates and inequalities. Okay, so you can think about any kind of mathematical subject from any of these particular subdisciplines of math perspective. Similarly, that's the case with mathematical logic. You could approach any sort of mathematical situation and keep in the foreground the idea of how things are being specified and described, and how does that affect what we can say about them. Okay. And you know, no man is an island, and no subject is completely disconnected from the other subdisciplines. Ideas from logic and these descriptive ideas combine perfectly well with other parts of math, as we'll see. Okay, so here's what I'm planning to talk about over the course of the lectures. So I'm going to talk about Lebesgue measure a little bit. I'm not going to assume basically any prior knowledge. I'll review things where I think it's common knowledge. I'll go quickly, but at least I want to set up the notation and refresh people's memories if necessary. So I'm going to talk about the classical Lebesgue measure, and then I'll talk about this effective analysis and how the effective point of view sort of penetrates and exposes some aspects of measure. And there's a couple of different traditions there. One you can sort of trace back to Martin Luff, and another one comes out of Kolmogorov's school in Russia. And we'll formulate both of them and see how they compare. Then this is the part where I want to sort of touch ground with sort of classical mathematical concepts, not motivated originally by a computational point of view, but motivated from the 19th century, motivated by Diophantine questions. So we'll talk about normality, which is tied to uniformity of distribution. A sequence, a binary sequence is normal if asymptotically every word appears with its expected frequency. It's a characteristic of a random sequence. And then the exponent of irrationality is a more technical number theoretic concept, but it has to do with the precision of rational approximation. And it goes back to Leoville. But we'll see what it is. And the thing about this choice of examples is that they align very closely with these two traditions in the study of effective randomness and effective analysis of measure. Then we're going to so this will get us at least through the first lecture. So after we look at those classical topics from the computability theoretic point of view and see what does the computability theoretic point of view contribute, then we're going to switch from just the pure subject of measure to this finer analysis of size given by dimension. Okay? And then review Hausdorff dimension, talk about the computability theoretic insights to the notions of dimension, and then we'll go back to look at these classical subjects from this point of view. And then finally, we're going to talk about what happens to sets at large. And there's some interesting distinctions between Lebesgue measure and the Hausdorff measures which underlie Hausdorff dimension. And there's some quite interesting open problems here that have a real logical component. So that's it in outline, where we're headed. So the main thing is some classical aspects of measure and dimension, right? The computability theoretic point of view, how does it apply to classical subjects, and then where might one go if one wanted to go further. That's the plan. Okay, so we start with Lebesgue measure and an effective treatment. So Lebesgue measure has to do with assigning size to subsets of, and I'm going to work with infinite binary sequences. So rather than moving to all sorts of different spaces, right, I'm going to stick for this discussion on the Cantor set. So the Cantor set is the set of infinite binary sequences. Okay? And I'm going to write that as 2 to the omega. So sorry if you have a different notation for that, but this is the one that I'm familiar with. I'm going to use it. Now I do get as speaker to decide some things for myself. Okay, so we're going to work inside the space of infinite binary sequences. A basic open set just is determined by a finite sequence, and you look at all the infinite sequences that extend it. Okay, so that's a ball. A basic, like an interval, a basic interval inside 2 to the omega is determined by some finite sequence. Okay? So all the infinite sequences that start off with 0, 1, 0. That would be a basic open set. And the size of that set, the set of things that start off 0, 1, 0, the size of that thing, well, 0, 1, 0 is a length 3 sequence. There are 8 length 3 binary sequences. And we're going to use the uniform measure. So the set of extensions of 0, 1, 0 has measure 1 over 2 to the 3, 1/8. Okay? Starting off with 0, that's half the measure. Starting off with 1 is half the measure, 1/4 of the measure, 1/8 of the measure, and so forth. Okay, then. So that's the size of a basic open set. Okay. You can take that notion, and now Lebesgue measure. The way that you assign measure to an arbitrary set, right, is look at the measure of a set A. Oh yeah, I have this cool little thing here. The measure of a set A, right, is the infimum, so it's the inf of the sum of the measures of basic open sets sitting inside some sequence of basic open sets whose union covers A. Okay, so you take this set, you cover the set by a bunch of open balls. Right? Each ball has a canonical size. Take the sum of the sizes of the balls that you use to cover the set, and that gives you an upper bound on the size of the set. Okay? Then the size of the set is the inf of all of those upper bounds. Okay, so you look at sort of optimal open covers and cover the set more and more closely by basic open sets, and take the inf of the size. This has a natural size. Take the infs of those natural sizes. Okay, so for the measurable sets, this infimum is called the measure of the set or the size of the set. So for every set there is an outer measure that is this infimum, right? And some sets there's an algebra of sets that behave nicely under this sort of measure. So the measure has the property, it's countably additive. If you have countably many disjoint sets, all measurable, then the measure of the union is the sum of the measures, and it behaves nicely as a notion of size. Okay. So that's the abstract a version of integral. Okay, now, the Lebesgue measure has the property that one says that it's regular. So what does regular mean? It means that the measure of the set A, as was basically defined on the previous slide, it's the infimum of the measures of the open covers of A, of the open sets that contain A. And the measure of A is supported, the size of A is supported by the sizes of its closed subsets. Because that's what regularity means. It means that if I have a measurable set A, right, A has some very simple subsets which contain arbitrarily much of the substance of A. Okay, so if A has measure a half, right, you can find a closed set. That's a very simple set. You can find a closed subset of A which has measure. All of its elements are inside A, and it's closed, and its measure is a half minus epsilon. For any epsilon greater than 0, you can fill A out by a very simple set. Okay, so that's in this case you say that the measure that the set A is capacitable. It has capacity. Capacity means it has closed subsets of arbitrarily well approximating its size. Okay, so the measure of so this is already a kind of, in a way, descriptive property, right? That's, you have an arbitrary set, you have no idea where that set came from, right? It's just a set. Right? But sitting inside that set, if the set has positive measure, sitting inside that set is something that's very simple. It's the complement of a union of basic open sets. Right? And that thing that sits inside of A carries the mass of A. Okay? So every set of positive measure has a very simple subset of positive measure. So that's the regularity of Lebesgue measure. Okay, now, good. So let's keep that in mind, right? That Lebesgue measure has this regularity property. So now I want to turn to the effective perspective. There were no descriptions here. I mean, there were open and closed sets, but there wasn't any kind of language or computations or things like that. Before we can dive into the computability theoretic point of view, we have to say something about what is the computability theoretic point of view. So I have to introduce a quantification of complexity of definition. Okay. This audience, it's mostly people in computer science, is that right? Everybody know what the polynomial hierarchy is, the polynomial time hierarchy? polynomial, NP, co-NP, etc. Okay, this is not dissimilar from that. Actually, this came first, but it's not dissimilar. I mean, what comes first depends on who you are. But so it's you can if you want to see something that's parallel to what I'm going to talk about, you could think about that. Okay, so this is called the arithmetic hierarchy, and it's a calibration. We'll start out thinking about it. It's a calibration of definable subsets of the natural numbers. And so I'm using omega to indicate the natural number, the order type of the natural numbers, 1, 2, 3, etc. Okay, so suppose that A is a subset of the natural numbers. Well, this is a mistake. I can fix that right away. It's a subset of a k-fold Cartesian product of the natural numbers. Okay. Then we say that A is sigma 0, 1, if and only if there is a computable, you know what computable means? Well, you're a computer scientist. Throw away the scientist, and you know what the computer is. So computable just means you could write a program and compute it, and there's no constraint on the running time or the amount of memory that's used. Okay, so that's what we're using the word computable to mean. Okay, so it's sigma 0, 1 means that there's a computable relation such that for all x is in A, if and only if there exists a y such that r of xy. Okay, and r is computable. That's sort of like NP, right? That there's a polynomial time procedure, and then something's in NP if that polynomial procedure can recognize a witness to the fact that it's in NP. Okay? So here there's a computable procedure, and it can be used to recognize whether there's a witness, right, for membership in A. Okay? So the canonical sigma 0, 1 set is the halting problem. The halting problem would be some program halts if and only if there is a computation that you can verify followed the rules of the algorithm. Okay, so the halting problem is the typical example of a sigma 0, 1 set. Okay, then you can build a hierarchy of definability, just like the NP, co-NP, and so forth. Now the hierarchy is, well, A is pi 0 n, so we've defined sigma stands for exists, pi stands for all. Okay, so exists 1 means it's existentially definable with a recursive matrix. Pi 0 n, if and only if it's the complement of a sigma 0 n set. Okay, so a co-RE set would be pi 0, 1. Sigma 0 n plus 1, if and only if there's a pi 0 n relation and the same feature holds, sigma n plus 1 means it's existential over something that's pi 0 n. Okay, so exists for all. All right, so sigma 0, 1 is exists. Pi 0, 1 is for all. Sigma 0, 2 is exists for all. Pi 0, 2 is for all exists. Sigma 0, 3 exists for all exists. Okay, so it's a count of the alternations of quantifiers. If you wanted to say something, so the halting problem says that the algorithm halts. Good. That's an instance of the halting problem. To say some computable algorithm halts on all inputs. Right? For every argument, there exists a computation that you can see ran the algorithm correctly. That's a pi 2. Right? For all exists. For all arguments, there exists a computation. Right? And so on. So this is a hierarchy that captures sort of the language of quantification over finite. Because the quantifiers are being, we're talking about elements of omega to the Cartesian product of copies of the natural numbers. Okay, so in that setting, I had a recursive predicate R. I could just as well have said, well, suppose I don't use something recursive, suppose I allow computation relative to a given set. So I'm doing some kind of computation relative to data. Right? If I'm given some x, some binary data, I could say, okay, R is being computed, but it could have access to the data. Sort of like, I don't know, there's a computation to display a movie on your computer if you're streaming the source from someplace else. Okay, so that's a computation relative to data. You're not running that thing by yourself generating the Marvel Cinematic Universe. Right? You need to have a source that's giving you the data, which you're processing locally and seeing the movie. Okay, so computation R could we just as well be viewed as doing some kind of computation relative to some kind of data. Okay, and then we could define the arithmetic hierarchy of things that could be defined from X. Right? Exactly the same form of definition. Okay. Or you could reverse your point of view and say, well, I don't want to think about generating a bunch of definable expressions, right, independently for each X. But I could switch it. I could think, well, maybe X is the variable, and I'm looking at what happens for the algorithm on input X. And to say that the algorithm does something on input X is a property of X. Okay, it's just changing which thing you're viewing as fixed, as a fixed parameter, and which thing you're viewing as an argument. Right? The syntactic form can work either way. Okay, so we have a hierarchy of definability, which we could view as defining subsets of the natural numbers, of pairs of natural numbers, or of a subset of 2 to the omega, a collection of x's, or a collection of natural numbers and x's, etc. It's a form of a definition, and there could be variables that are number variables, there could be variables that are real variables. It's a syntactic form. That's the arithmetic hierarchy. Okay. And this comment is just that you could view the number as an argument, or you could view the data as an argument. And either way, you can talk about a definable subset of 2 to the omega or a definable subset of omega. Okay. Good. And so forth. Good. That's the comments I've already made. All right, now, let me give a couple of natural examples, and then I'll pause, and you can ask a question if you want to. Okay. So first of all, if A is a subset of omega, A is sigma 0, 1, it is defined by an expression in that form if and only if A is what's called computably enumerable. There's a program which you could start, and it will start to enumerate a sequence of numbers, and what it will enumerate are exactly the elements of A and nothing else. Okay. So why is that? I have a definition. X is in A if and only if there exists a Y such that R of xy. Okay. Now suppose you wanted to enumerate all the elements of A. What would you do? I can't speak to what you would do, but I know what I would do. Right? What I would do is I'd say, well, let me just check. Is 0 in A because of Y? Does R of 0, 0 hold? In which case, 0 is the witness that 0 is in A. Okay? If yes, enumerate 0. If not, well, then let me check. Is 0 in A because of witness 1? If so, anytime the answer is yes, enumerate the number. How about 1? Is 1 in A because of witness 0 or witness 1? Each one of those things you can compute because R is computable. And now how about 2? Right? Is 2 in A because of witnesses 0, 1, or 2? And how about 0 for witnesses, I already checked 0, 1, now I'll check 2. And how about 1 in A by witness 2? So you can the set of pairs of natural numbers is a countable set. You can just run through all the pairs, and whenever you find an instance of Rxy, enumerate X. Basic open set is determined by a finite sequence. So if I wanted to describe an open set, all I would have to do is specify all the finite sequences, so that open set is the union of the balls that are determined by those by those finite sequences. Right? So the open set O could be described by O consists of the union of the ball determined by sigma 1, the ball determined by sigma 2, the ball determined by sigma 3, and so forth. The sequence sigma 1, sigma 2, sigma 3, and so forth, that's just counting much information. That's the sort of thing that a subset of 2 to the omega can know. I mean, that an element of 2 to the omega can know. Okay? So infinitely much finite information is something like this. And that's all you need in order to tell membership in O. Okay? And conversely. Good. If X is omitted, in other words, if I just have a sigma 01 definition, not relative to any data, that's what we call an effectively described open set. There's an algorithm which will tell you sigma 1, sigma 2, sigma 3, and so forth, so that the open set is the union of the balls determined by sigma 1, sigma 2, etc. So an open set is described as a union of open balls. It's effective, right, if the sequence of open balls can be algorithmically defined. Okay. And then this is a typical bit of vocabulary. A Pi01 class is just the complement of an effectively presented open. It's the complement of an effectively described open set. In other words, it's an effectively described closed set. And good. Pi01 class is effectively presented closed set. Okay, good. Any questions? Yeah, go ahead.
For the first one, it's kind of clear because I can take union of open sets.
This one here.
Yes.
Yeah, so it's if O is, so which direction? So if it's sigma 01 relative to X, right, then we want to say that it's open. And the reason is that something is in O, right, because, let's go back to the form of sigma 01. This is computable from X, right? And I want to, let me go to here. Okay, so here I have to sit down for this. I don't have a good notation written up there. Okay, so what have we got? We've got sigma 01 relative to X means Y is in O if and only if there exists some little y in omega such that something is computable from little y, y, and x. Right, so this is a sigma 01 relative to x subset of 2 to the omega. Okay, where this is something that's computable. Okay, so to tell that y is an O, you run a computation, right? And that computation converges on some relative to some integer. Well, the computation only uses finitely much about y and about x. It's normal sort of computation. Okay, so anybody who starts off in the same way that y does, right, will evaluate that computation the same way. Okay, so the way that y makes this thing computable, the way that y makes this computation converge is only specifies finitely much of y. So it will apply the same reason of membership will apply to anything that starts out in the same way that y did. Anybody who makes that computation converge is going to be in the set. In other words, the whole open ball of things that looked like y long enough to get this computation to be evaluated is going to be contained in the set. So the set's open.
Yes, but the second point,
This one,
pi 1, 0 behind 0.
this.
So, is it because closed set is just a complement of open set?
Yeah. And an open set is sigma 0, 1, and pi 0, 1 is the complement of sigma 0, 1. Okay.
So yeah, question. So there is an X and there is an R. So like what are they? Like
Here.
yeah. So like I can come up with what should the R and X be.
Yeah, so in this example, R is something that's computable. And the little x and the little y are natural numbers.
Yeah, but the open.
Yeah, so then down here, when we replace, right, the computable R with computable relative to x, that means you're allowing x as an oracle or fixed. You're fixing x as data, and now you're doing the computation, but the computation gets to query membership in x. It gets to ask what's the nth entry in x. So that's does that answer the question?
I mean, could you go to the next slide?
Here.
Yeah. So the second dot. So there is an x, and I imagine there is an rx, right?
Yes, that's right.
And what are they?
Yeah. So the sigma 0, 1 relative to x would mean that let's say y. Now we're talking y is in. Oh yeah, it's here. Y is in O, if and only if there exists, in this case, sigma 0, 1, so there exists some natural number, right, such that this, and now that thing, is something that is computable, right, in both the pair y and x. So there's one algorithm here. Let me erase some of this stuff. Think of R as being described by an algorithm. Okay. Now, when you run that algorithm, right, you're going to run it using these two things. Those two things are infinite sequences. So you get to use them as data. You get to query them. Right? What's the value at k? What's the value at l? Right, etc. So you can query these guys. But this is a normal algorithm, a normal computer, written in C++ algorithm. Right? And then to say that there exists a y such that this holds means that the algorithm on that input y has to return a value and say that the computation accepts.
Okay. I mean, could you provide some example?
Yeah, sure. Okay, so let's take the example which says. Okay, how about the example that says what there exists? So, all right, let's see. Okay, how about this one example? There exists some y such that y and x agree between y and 2y. Okay? That's an example. Right, so then the set of y's that would satisfy this are the ones that we're identifying blocks inside x, right? The block between 2 and 4, the block between 3 and 6. Right, so the set of y's that are going to be inside this set are going to be the y's that agree with x on one of those blocks. Okay? So, and you can see this is a countable union of basic open sets. Each y gets into this set because some finite thing is true about y and x together. Okay. Okay, any other questions? Okay, good. Okay, so I'll stand up again. So now, let's go back to measure. Now, this is, I think, a kind of interesting line of investigation, not due to me, from the 1960s or so. So we'll say that a sequence, this is an infinite binary sequence, is Martin-Luff random. As you can guess, this was defined by Martin-Luff. If and only if, so it's Martin-Luff random if and only if, and now I'm going to say it sort of imprecisely. It doesn't belong to any effectively presented null, measure zero, G delta set. Okay. So precisely. So this is if you're familiar with this G delta notation. If you're not, you don't pay any attention to that sentence. Okay, so precisely it means if you have a sequence of uniformly, effectively, a sequence of sigma 0, 2 sets, sigma 0, 1 sets, uniformly presented. Okay, so I have an algorithm which will tell me what's the first, what's the second, what's the third. And the measures of these sets are shrinking to 0 geometrically. So the measure of the kth set is less than 1 over 2 to the k. Okay, so I have a sequence of open sets that are getting smaller and smaller, thinner and thinner. Okay? Belonging to the intersection is measure 0. Because the intersection has measure the limits of the sequences that are converging to it. Okay? So this is an effectively measure 0 set. Right? Random means you don't do anything that happens almost nowhere. Okay, so Martin-Luff random is don't belong to any effectively presented measure 0 set. So the elements of this intersection, right, have some effectively described non-random property. Right? If you pick a number at random, it's not going to be in this definable measure 0 set. The complement of this set has full measure. Okay, so almost every real is not inside that set. Okay, so, but the set, right? These kinds of properties, it's a reasonably big collection of measure 0 sets. Right? If you can sort of computationally figure out something that is anti-random, right? Well, it's going to end up with some kind of null set like that, and a Martin-Luff random will not exhibit this computationally pathological property. So we'll give a couple of examples. Yeah, go ahead.
It's same as saying that there is no Turing machine which given n.
Yeah, so it's uniformly means, so I think of this as a presentation of an open set. Right? An open set is determined by a countable sequence of balls. Okay, so I have an algorithm, right, which on input k will tell me all the open balls in the kth set. That's uniform means there's one thing that can take k as an argument and then tell you the description of the open set. Okay, so you have one way to compute a sequence of sets. Right? And the way you're specifying the set is by specifying the basic open balls that make it up. Okay, so a Martin-Luff random is a real number that doesn't exhibit any of these measure 0, effectively described measure 0 properties. Okay, so that's one way to talk about randomness. A random thing, let me go back here. A random real is not going to belong to this concretely described measure 0 set. That's okay. Now I can just say that, but we're taking if you take any measure 0 set, you could think of it as a way in which reals could be non-random. Right? It has no measure, so almost every real doesn't belong to the set. So when you want to pick out what measure 0 sets have a kind of universal property that they capture a certain family of non-randomness. Okay? The Martin-Luff method is to write down these sorts of null sets and say something is effectively random if it doesn't have doesn't belong to a null set which is described this concretely. Okay, there's a second approach. Right? The second thing that happened so you could say a random real avoids null sets. Another thing that a random real does is that all the digits in a random sequence are chosen independently at random. Right? That's the typical example of randomness is you take a fair coin and you repeatedly flip it, and that tells you a sequence of heads and tails. Each flip is independent. Right? The probability that you'll get a heads or tails at step k is independent of what happened at steps 1 through k minus 1. Right? If you were to look at a random image on your television screen, it just looks like what we call noise, white noise. Right? There's no patterns there whatsoever. And if you wanted to describe to someone exactly what you were seeing on your TV screen, you would have to tell them pixel by pixel exactly what is at each point in the screen, because there's no correlation between one point and another. Okay? So that was Kolmogorov's, and then it was done independently by Chaitin in the US. But it was, the idea there was a random sequence, there's no patterns to it. So if you have a sequence that's random, you can't sort of give a short description of how to generate a large part of the sequence. It's indescribable. The only way that you could specify the only way you could communicate the first k digits of the sequence is basically just to say what they are. Right? You can't say something like it's zeros except at the powers of 2. That's not random. Right? Or every other digit is, here are the odd digits and all the even digits are 1. That's not random. Any shortcut to describe what the sequence is doing is a way to exhibit a failure of randomness. Okay? So now you can formulate a criteria for randomness by saying there are no shortcuts in the descriptions of the initial segments of the sequence. Now, what's a description? Well, we have calibrated what descriptions mean. Right? We have a hierarchy that describes what definability is. We can measure the complexity of descriptions. Okay? So here we go. If sigma is a finite sequence, k of sigma is the length of the shortest program which outputs sigma and then halts. Right? Okay, in some nice universal machine. So you have a map that maps. You have a map that maps finite sequences to finite sequences, and for technical reasons, you require that map be prefix-free. So if the map is defined on argument sigma, it's not defined on any initial segment of sigma, proper initial segment, and it's not defined on any continuation of sigma. Okay, so that's the complexity of, let's see. K of sigma is the length of the shortest program which outputs sigma. Okay, so if you look at the sequence that's 0 except on the powers of 2, and I want to know, if I wanted to know what is that sequence up to length L, the complexity is essentially the complexity of L. Right? Because I have a nice algorithm that will tell me what the sequence is up to L. Right? If I had a sequence which was 1 and all the even numbers, right? Well, then the complexity of that sequence is going to be about as complicated as the complexity of the digits on its odd part, because the evens, right, are all 1. Okay, so its complexity is going to be no more than half its length. Right? Okay, so on. Then, a sequence is algorithmically incompressible if and only if there's a constant such that for all L, the first L bits of the sequence has complexity L minus a constant. Okay, so up to an additive constant, in order to specify the first L bits of the sequence, right, you might as well just say what they are in L many statements. Just take the sequence as data. Right? There's no faster way to generate the sequence. Yeah, go ahead.
So, this particular is like, if you fix all the events to be 1 and others to be random, this will become n by 2.
Yeah, right. Yeah, that's right.
Can this be in some sense like a measure of randomness?
Yeah, that. We'll come back to that when we talk about a measure of dimension, right? So that kind of sequence, which is random on the odd parts and fixed on the even parts, that kind of sequence we're going to say has effective dimension 1/2. Okay? So, and then we're going to connect it to notions of geometric measure and Hausdorff dimension. So that's right. So it's this notion of randomness is the notion tied to Lebesgue measure, which is dimension 1, right? And if you sort of cut the complexity by 1/2, you're going to end up with something that has dimension 1/2. That's how it works. Okay. Then there's a theorem from the 1970s that says the two ways of calibrating randomness agree on the sequences that they identify as random. So a sequence is random if it avoids all these nicely defined null sets. It's random also if it's incompressible by any, it's algorithmically incompressible. So the two notions of randomness. One is you could sort of think of it like a statistical aspect of randomness, and the other one is a descriptive aspect of randomness. Those two things agree on which sequences they identify as random. So that's a kind of pleasing fact, right? That there is some evidence there that this notion of randomness is not an extremely fragile concept. Right? Because you could come at it from completely different conceptual points of view and end up with the same, different intentions and the same extension. Okay. Okay, so any questions? Yeah, go ahead.
I don't see this sequence which is 1 and even. It's not Martin-Wolf.
It's not Martin-Wolf random because you can look at the measure of the among all the, look at the basic open set, right? We want to see if all the digits, all the even digits are 0. Okay, all the even digits are 0. Right? Then let's look at a sequence of open covers. The first open cover is the ball of the sequence that starts with 0. Well, I guess even. The ball of the sequence that starts with look at the two sequences. 1, 0, oh no, yeah, that's, and 0, 0. Okay? That covers the set. Right? Because the second digit is 0. Right? So we looked at, if you look at something, so we want to look at the second digit, this is digit 2. Right? Those two, anybody who's all whose even digits are 0, right, has to go through one of those two balls. That has measure 1/2. Right? And then we've got something that looks like this. Right? Right, so now we're up at level 4. There's 4 balls that cover the set, but there's 16 balls. Now we're at measure 1/4, and so forth. So you can cover the set of things that are 0 on the evens, right, can be covered in a canonical way by a sequence of open sets whose measures, the kth set is measure 1 over 2 to the k. Okay. Well, are we? Okay, good. Okay, good. Now, so let's look at how this kind of notion of defining randomness for a point, right, connects to the notion of measure of a set. Okay. So, if you have a closed set, right, it can be represented as the collection of infinite paths through a tree of finite sequences. Right? Take the tree of finite sequences, terminate all the nodes that correspond to balls in the complement of the open set. Any path through what remains is in the closed set. Okay. When this tree is computable, C is a pi 0, 1 class, and otherwise C is pi 0, 1 relative to T. Right? If you have a computable tree, to say that X is a path just says for every L, the initial segment of X up to the first L bits is an element of the tree. That is a for all computable definition. Okay, so the paths through an infinite binary tree are a pi 0, 1 class. They correspond exactly to the closed sets. Okay, so here's our first theorem.
Sorry, how can there be infinite paths in a finite sub?
No, it's a subtree of 2 to the less than omega is all the finite sequences, all the finite binary sequences. This consists of, this is less than omega means arbitrary length binary sequence. Okay, so an infinite, like for example, let's take all the finite sequences, and then any infinite binary sequence, its initial segments all belong to the tree of all finite sequences.
Okay, and how do they form a tree?
Under extension.
Okay, I see.
You just, the longer one it extends the shorter one. Okay. Okay, so now here's the fact. If C is a pi 0 1 relative to T, so C is a closed set that is definable from T, right? Then C has positive measure if and only if it has an element that's Martin-Luff random relative to T. So if you look at a closed set, and you take T as the description of that closed set, then the closed set has positive measure if and only if, right? The set has a single point, which is random when evaluated relative to T. Okay, so you can analyze whether the set is null by asking, does it have a random element, or does a random element? We defined randomness using Martin-Luff's point of view by saying that the path avoids all small intersections of open sets. But then you can prove if you have a closed set, right, it has positive measure if and only if it has an element that can avoid all the small open sets. Okay, and good. Now, okay, so this is an exercise. Okay. Now the interesting thing though is that this applies to an arbitrary set. So you can look at an arbitrary set and ask, does it have positive measure? Well, and the answer is it has positive. I'm going to look at the elements, right, of the set out of context. I don't want them to, I want to look at the elements point by point, right? And not talk about open covers of A. I want to look at the quality of its elements and see, does it have positive measure? And you can do that in the following way. A has positive measure if and only if for every T, for every infinite binary sequence, there is an element of A which is Martin-Luff random relative to T. Okay, so no matter what data you take, there's an element of A that's random relative to that data. Okay, so A is positive measure if and only if, relative to any data, it has an element that looks effectively random. All right. That's rather nice. We can analyze whether A has positive measure just by looking at pointwise. What are the pointwise features of the elements of A? Okay, this is now, all right, now. How might we see that this is true? Okay. One proof, the easier proof, right? Assuming that you've already agreed to everything that I said so far, right? The easier proof is, oh look, I have an arbitrary set A. If it has positive measure, right, then it has a closed subset that supports its measure. Right? That's the regularity of measure. An arbitrary set has positive measure means that it has a simple subset, which approximates its measure from the inside to arbitrary precision. Okay, so if A has positive measure, then it has a closed subset of positive measure. But for closed subsets of positive measure, that's this. That's this thing that I said was an exercise. Closed subsets interact well with the notions. Closed set is a pi 0, 1 class. It interacts well with effectively presented open covers and so forth. Right? So you can use the fact that it has a definable subset, right, and analyze how the specification of the subset works relative to the definition of random by Martin Love. Okay, so that's one way to do it. That's the way I prefer. Okay. Now, on the other hand, you could dig into the definitions, right, and do it all from scratch. Okay, so you could dig into the what does it mean to have measure 0? Well, that's something that's described in terms of open sets, et cetera, et cetera. Right? And just deconstruct the whole situation and then reconstruct it to get the conclusion. But the shorter proof is to use the fact that Lebesgue measure is regular, and so A must have a simple subset. And simple subsets can be analyzed in a straightforward way. Okay, so how do we stand on time? That ends the first part of the lectures, right? Lebesgue measure and the effective theory of Lebesgue measure. Okay, so I guess we're going to take a break in about 10 minutes. So let me tell you a little bit about these historical precedents of aspects of randomness, and then we'll take our break. Okay, so randomness it's one of these fundamental mathematical properties, right? Like concepts like size, shape, etc. Right? Randomness is another sort of primitive mathematical aspect, right? And it has been investigated from every mathematical point of view, and it's still under investigation. You know, there's all kinds of interesting problems about, can you use a random oracle to speed up some class of computations? It shows up in various Monte Carlo methods. I was told by a student of Kolmogorov that the reason Kolmogorov investigated Kolmogorov complexity is because Kolmogorov wanted to prove that he wanted to find randomness in fluid mechanics. He wanted to show that turbulence, the phenomenon of turbulence, had an irremovable randomness aspect. So randomness shows up, all over. Okay. Now, there's a very close parallel between the sort of descriptive aspects that we've been trying to evoke to describe measure and randomness, and things that came earlier in the context of Diophantine approximation. Okay, so Diophantine is numbers, right? So Diophantine approximating infinite things by discrete things. That's Diophantine approximation. It deals with the approximation of real numbers by rational numbers. Computability, it involves when we typically, like in this hierarchy of definability and so forth, the basic objects that we are studying are the things that are computable, and we're looking at how an arbitrary real might be in Kolmogorov complexity approximated by an algorithm, by something you compute algorithmically. So instead of it being approximated by rational numbers, we typically look at the behaviors as reflected by their of a real, how does it behave in its interaction with computable phenomena, or more generally, some kind of definable phenomena. Okay, so there's some crude parallel there. I guess approximation shows up in two places, right? And a rational number is a particular kind of computable number. Okay, so here's the first sort of classical property of randomness that I want to discuss, which is called normality. Okay? So this is due to Borel from 1909. And this was a precursor to the law of large numbers. The law of large numbers says if you have some experimental, suppose you have some experiment, right? And you repeat the experiment, and you can duplicate it. You repeat it over and over, right? Then the outcomes that you observe will asymptotically converge to the expected values. Right? You flip a coin, a fair coin, right? Each flip, you either get a 0 or a 1, you either get a heads or a tail, right? That's discrete. But if you repeat the experiment of flipping that coin and record your results asymptotically, right? The ratio of heads to the number of flips is going to go to a half. That's what it means to be a fair coin. Okay, so that's, now, a number is simply normal to base b. So we take a real number is not a binary expansion. It's not a decimal expansion, right? It is an element of the continuum. Okay, so the real number is described, right, by some kind of base b. It could be binary or base 10 or octal or you name it, right? You fix a base, and then you can describe a real number in terms of its base b expansion. Okay? The real number is called simply normal to base b if in its base b expansion each digit occurs with limiting frequency 1 over b. Right? So the number whose binary expansion is 0.01010101, etc., is simply normal in base 2. Right? Half the time it's a 0, half the time it's a 1. Okay. A number is normal to base b if you don't look just at the digits. That's the simple case. You look at the words, the blocks of digits. And each block of digits shows up in the base b expansion, its expected value many times. Well, if the block has length L, right, there are b to the L many blocks of length L, right, and each one shows up 1 over b to the L in frequency in the base b expansion. Absolutely normal means that this feature of normality is true for every base. No matter which base you choose in which to represent the number, right, you get something that so that the digits and the blocks are equally distributed. Okay? So simply normal is a single digit. Simply normal to base b is a single. You look only at single digits in base b. Normal is you look only in base b. Absolutely normal is you look across all integer bases. Okay? So this property of normality, it's not merely a property of the real number c. Right? It's a property of how we choose to represent c. right? So looking at a base B expansion to represent a real number is a particular way of choosing a sequence of rational numbers that approximate that real number. It's a particular form of a Cauchy sequence. Okay, so this is it's a feature of the representation of numbers. And the set of numbers that are absolutely normal has Lebesgue measure 1. Okay. I wrote down here, this is an exercise. This is it's not too hard, but it's a way to understand what normality means. If C is normal to base B if and only if you look at the sequence of numbers that you get by iterated multiplication by B, that sequence, and you take the number, right? Look at its fractional part. Multiply that by B. In base B, you're shifting by 1 digit. Throw away the lead digit. Look at the fractional part again. You get another number between 0 and 1. Multiply by B, you get another number between 0 and 1 after you look at the fractional part. Okay, so a number is normal if and only if this generated sequence by iteratively multiplying by B is uniformly distributed in the unit interval. Okay. So this is another way to, instead of looking at words and so on in some sequence in the alphabet with B letters, you can look at the action of multiplication, mod 1. Those two notions are the same. Okay, so Borel proved almost all real numbers are absolutely normal. Okay, so he proved that a random real, right, is absolutely normal. It doesn't matter what base you choose to represent that number. You're going to produce a sequence where all the combinations are equally distributed. If you choose a real number at random. And then Borel proved almost all real numbers are absolutely normal. Being not absolutely normal is a measure 0 set. And then Borel posed the problem. Give one example. So give any example of an absolutely normal number. So I once heard a nice talk about this kind of thing. And the problem here is sort of, well, you have a haystack, right? The haystack is all the real numbers. There's a giant stack of hay, right? And what's the problem? Right? The problem is exhibit a single piece of hay. Right? Every number you can think of, you pull out, it's a needle, it's a needle, it's a needle. Right? The problem is something happens almost everywhere. Let's give any example, a concrete example. Okay, so it's not known whether any of the familiar, so rational numbers have repeating expansions. Those expansions are not normal. If the expansion is eventually periodic, it can't be normal. That's one to sort of, if you don't want to pay attention to what I'm saying, you can think that one through. Are any of these familiar irrational numbers normal? Absolutely normal. Is pi absolutely normal? E, the golden ratio, the square root of 2. Right? Anything. Are any of those normal? Borel conjectured in 1950, he had to think about it for a while. But by 1950, he conjectured that all irrational algebraic numbers are absolutely normal. That problem is open. It's open whether pi is absolutely normal. It's open whether E. It's open whether algebraic whether irrational algebraic numbers are absolutely normal. So all the numbers you know, it's open. I guess except for the rational numbers. Okay. The first constructions, and I'm not using this in a loose way. I'll end with this slide and we can go get a snack. Okay, so the first definitions, I'm going to do it that way. The first definitions of absolutely normal numbers were given by Lebesgue and Sierpinski. I'm a great admirer of Sierpinski, by the way. So they were given by Lebesgue, and they did it independently. They had essentially the same idea, and they published it simultaneously in the same journal on contiguous, where one was published directly after the other in the same volume. So the two papers appear side by side, and they both give examples of absolutely normal numbers. So their example was essentially this. Look in the unit interval. Take the collection of absolutely normal numbers. Okay? It has measure 1, because being not absolutely normal is a null set by Borel. So I have a measure 1 subset of the unit interval. It has a closed positive measure subset, right? Because Lebesgue measures capacitable. Okay, so now we have a closed subset of the unit interval. Well, what do you know about, and we can define it. We have this, and they were concrete about how they defined the closed set. Okay, so they had the unit interval, throw away non-normal, then define a way to build a closed subset of that set. Now I have a closed, definable subset of the unit interval of positive measure. Well, you have a totally bounded closed set in the real numbers. It has a least element. Yeah, go ahead.
What happens after the nine?
Oh, in this thing?
In this number, yeah.
Oh yeah, I'll get to it in a second. Okay. So I'm still up here. Exhibit a closed subset of the unit interval. Right? It has positive measure, so it's not empty. Its least element is definable. That was their example. Okay. That's not a very convincing example. It was a definable real, but the apparatus to define it, right, was fairly, it was defined from the outside, not from the inside. Okay, so we'll get to this. We'll come back to this later. Okay, so Champernowne's number. Champernowne's number is obtained by concatenating the base 10 representations of all the integers in order. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. That's Champernowne's number. Okay? So Champernowne's number is, it's simple to describe. It's elementary, but this is a kind of understatement. It's a fairly complicated argument to prove that it's normal in base 10. But it is. Okay. All the patterns show up. And I'll give a picture of this later. Okay, so it's normal in base 10. It's not known whether it's normal in any other base. It's explicitly made to be normal in base 10, and that's everything that anybody knows about it. Yeah, go ahead.
Is it known if there are numbers that are normal in one base but not normal in the other?
Yeah, I'll get to that. I'll get to. Yes, the answer is yes, there are, and I'm going to come back to that. So thanks for asking, but we'll see more about that as time goes on. Okay. Yeah, go ahead.
This construction by Lebesgue and Sierpinski, is this number computable?
No.
So does it involve the axiom of choice or something like that?
You anticipated the next slide. Right? So I'll say it since you anticipated it. So Alan Turing, should we say the first computer scientist, proved, and I'm putting here circa 1938, there is a computable absolutely normal number. And, he didn't publish this result. It was found in his papers, It's published in his collected works. It was handwritten manuscript. He worked it out and he sort of kept it. He didn't publish it. Okay, now in his handwritten manuscript, his notes, there was one point in the argument which he just asserted, and which later people haven't been able to verify. So in the calculation, in the estimates that he made. And a slight change, right, is something that these authors, Becher, Fagela, and Pichi, worked out. And they published an account of Turing's algorithm in 2017. Other examples were given by Wolfgang Schmidt in the 60s, and then the Sierpinski method was made algorithmic by these two people, published in 2002. Okay, so there are computable examples. Turing, on his manuscript, comments that this is an algorithm, but this algorithm will never be implemented, because it was something like double exponential time, or even maybe a bit worse. Okay, so it was a not a feasible algorithm. Okay, so I was hoping you can see 78 slides, and we made it through 20. I'm going to have to maybe after the break, I'll lecture a bit more, and then we can answer questions and do that. Okay, so let's go get some snacks. Sorry to run into break time there. All set? Okay. Well, thank you everybody for coming back. All right, so we ended with this theorem of Turing, who gave an algorithm to compute an absolutely normal number. Like I said, there were other instances by Schmitz and Becher and Fagela. But then sort of the natural question there is, the question was, give an example of an absolutely normal number, right? The best so far approach to that, it'd be better to show square root of 2 is absolutely normal, because that's an extremely concrete specification of a natural number. The best that we know so far is that you can get numbers in polynomial time. You can write a polynomial time algorithm, in fact, and then this was even improved more recently to get to be subquadratic. But a few years ago, Becher and Heiber and I we gave an algorithm for an absolutely normal number C, such that for any base B, you can compute the first n digits in the base B expansion in time n squared. So I'm going to say something about how this proof goes. So the main ingredient in the way that this construction goes is that Lebesgue measure is uniform. Right? It's something that's translation, and it's invariant under scale and invariant under translation. So if you took, let's say if you took the full binary tree and you mapped it by putting k many zeros in front of the root and stick it inside the tree. So now I'm looking at a piece of the binary tree that has measure 1/2 to the k. Right? That map is this kind of rigid translation, and it changes the scale. It preserves measure. There is an isomorphism up to change of scale between the tree and all of its parts. So the way at which a sequence is normal in the tree, right, is reflected by the way that it, over some start, looks normal afterwards. Okay, so there's a homogeneity in the tree. The tree is isomorphic to all of the open restrictions of the tree above any point. So the way that almost every sequence becomes normal is homogeneous. It's translation invariant. Okay, so here's a sketch. Now I'm going to give a proof sketch, which means I'm actually going to sketch. Okay, so here we go. Now I want to build something that's normal. So that means that let's think about it for first normal in base 2. Okay, so we know how to have a sequence that is simply normal in base 2 for words of length 1, 0, 1. Right? So you could write down a sequence that is simply normal. You know, it's 0, 1, 0, 1, 0, 1, 0, 1. Okay, now if I go with that sequence for a long time, so this is here we can take words of length 1, okay, and have them be equally distributed among the digits, okay, all the way up to here. Yeah, go ahead. Sorry, what?
Could you please clarify what we are proving?
Oh yeah, we're proving this theorem. I want to give an algorithm that will produce an absolutely normal number, and I want to do it efficiently. Okay? So I don't want to run out of room here. Okay, now the next thing that we have to worry about, so we could do this for a long, long time. Just equally distribute the digits 0 and 1. That resulting inside that sequence, right, then if I do 0, 1 alternately, I'm not looking normal, right, for words of length 2 because the word 0, 0 is not appearing. Right, 0, 1, 0, 1, 0, 1. The block 0, 0 has not appeared yet. Okay, so now, but we can do this. We can give a very simple description of what we're going to do for a long time. Okay, so we're computing the digits very rapidly. Now the next problem is after we've done this for the lifetime of the Earth or something, we've done it for a long time. Now I want to start working on words of length 2. Okay, so suppose now, how many digits does it take, right, to get something that is normal? You know, each word of length 2 occurs with the same frequency. Or let's say occurs with frequency 1/4 plus or minus a minuscule amount. Okay, well that is an invariant. How many digits do you need before you start to look normal for words of length 2? That length is invariant over, if you start at the very beginning and try to do that, or if you start at some point on, how many more digits do you have to specify so that the little piece that you've added on here, this little piece, is normality for words of length 2. You don't need that many digits to have equidistribution for words of length 2. You can make sure that this blue part, this little part that you're going to add, so as to make the words of length 2 equally distributed, you can make sure that compared to the long red length is very short. Okay, so now, if I look at this red plus blue sequence, right? It's almost normal for words of length 1 because the blue part is so short compared to the red part. So if I'm looking at some place inside here, it's almost all red, so the digits, the single digits are almost equally distributed. If I look here, the single digits are equally distributed because the length 2 digits are equally distributed there. And if you have the same frequency 0, 0, 1, 0, 0, 1, 1, 1, you're going to have the same frequencies of zeros and ones because they balance out. 0, 0, 1, 1 balance, 0, 1, 1, 0, they're already equally distributed. So when you get in this initial segment, when you get to here, everything looks good for words of length 1. If you're looking inside there, well, the red part completely dominates. So you look good for words of length 1. Right? And now if you do this, and now this part turns into epsilon and this becomes gigantic, then the whole sequence looks good for words of length 2. Because the red part can eventually get dominated by the blue. So you look good for words of length 1 for enough time that the momentum that you have on words of length 1 can get you across any little blue interval. And then you repeat the blue intervals until the momentum that you've got in blue can get you across any little interval for words of length 3, and so on. Okay? So that's the picture of the algorithm. Right? And figuring out what to do here just means you have to figure out what is the appropriate little blue line you want to add. And that computation of what should I do here is a lot shorter than the amount of time that you've allocated for yourself, which is the length, the place of the digit that you're working on. So you can pad the time. That's the idea. You can do something really simple to compute for a really long time. And now to compute this digit, well, I have k-squared amount of time to use to compute what to do with this digit. Well, that gives me enough time to figure out what the blue thing should be. Because the blue thing is scale independent. The length of that blue interval is scale independent by the homogeneity of Lebesgue measure. Okay, so that's, in outline, that's the combinatorics of it. Any questions?
What about absolute number?
So good question. So now we want to do this. We were talking about base 2. Well, now we know that almost every real is normal in both base 2 and base 3. So that means I could find some rational among all the possibilities here. I don't know. I guess the short answer is you can make this blue thing so that the result of appending that blue, the result of what is the blue thing really doing? It's telling you a rational interval to which the real should belong. Right? So instead of thinking I'm building a sequence, a binary sequence, I'm really going from here I have a rational interval, and then I have here a rational interval, and I want to choose a rational subinterval. Right? And that's the blue line. Okay? What you have to do is you have to choose a rational subinterval so that that blue sequence appending the expansion for both bases is something that is normal for words of this length. But that's something that is a measure 1 property. And so if the length, if the change in scale is sufficient, there will be a sequence, there'll be a subinterval here so that the binary extension and the ternary extension are both normal, sufficiently normal. And then you have to do the algorithm so that you time it right. How many bases am I going to consider when I build the blue line? How much normality do I want to achieve for those bases? And you can add in the bases and the degree of normality at your own pace. So you add those bases and normality in at a pace such that the amount of time you allocate at each point for what to do is greater than what you need to do to figure out which subinterval to choose. So it doesn't matter where you are, this length, what fraction of the interval you're looking at will be acceptable is always the same by homogeneity. Right? But you can pad the time by making this red thing as long as you want. Okay, so you can wait until the index for the digit you want to find is so great that it swamps the length of computation you have to do to figure out what to do next. So it's sort of, you know, you can sort of think of it as do what you did when you were a kid until you're old enough to do better, right? And then when you're old enough to do better, start doing better until you're older than that to do even better. And that's sort of the picture. Yeah, so you do it first for binary, then you wait until you're looking at an index, a digit length, that it's sufficiently large that you can figure out what to do for binary and ternary. And then up here someplace, binary, ternary, and quaternary, and so forth. Okay, so that's the sketch. Okay, if something is supposed to be feasibly computable, then you should compute it. Here's a picture of so each pixel here is telling you a digit, right? These are digits in base 10. The number that we worked out starts out like that. This is a depiction of the first, 250,000 digits. Champernowne has interesting patterns, right? It's got this kind of, it's repeating small digits, and then it puts down a first digit, and then et cetera, et cetera. This is the pattern for Champernowne, and that looks much more random. But it's just a picture. But it is possible to actually write the program and run it. Okay, so we asked about the question came up. What about normality in different bases? If a number looks random, if a number is normal, which is a characteristic of randomness, if it's normal in base 2, does that tell you that it's random enough to be normal in base 3 or what? Okay. And so that question came up in the realm of number theory. And there's one easy connection to see between normality in one base and a normality in another. For natural numbers, B1 and B2, B1 and B2 are multiplicatively dependent if they have a common power. Okay, so 4 and 8 are multiplicatively dependent. Right? They're both powers of 2. Right? So they both have a common power. Okay. 2 and 6 are not multiplicatively dependent. Okay, 6 has a prime factor that's not 2, so they can't have a common power. Okay? So it's not relatively prime, it's a different notion. Okay? Then a theorem of Maxwell says if you have two multiplicatively dependent bases, then for any real number, it's normal to the first if and only if it's normal to the second. So a number is normal to base 8 if and only if it's normal to base 4. If and only if it's normal to base 2, etc. And then Schmidt, in the early 60s, proved there was a theorem of Cassell's too. Cassell's showed that if you take the Cantor middle third set, right, which is take the unit interval, throw out the part between 1/3 and 2/3, then repeat that process on each of the remaining intervals iteratively. If you look at an element of the Cantor middle third set, what can you say about its expansion in base 3? Well, the first digit must be either, this is between 0 and 1, the first digit has to be 0 because you're in the first third, or it has to be 2 because you're in the last third. 0, 1, 2, the middle third is digit 1. Okay? The second digit must be either a 0 or a 2. 0 or 2. An element of the Cantor middle third set is not normal in base 3. It does not exhibit, right, the digit 1, right? So the digits are not, the digits 0, 1, and 2 are not equally distributed because 1 never shows up. Okay. However, if you take a random element of the Cantor middle third set, give the Cantor middle third set the uniform measure, the first third gets measure a half, the last third gets measure a half, and keep splitting them. Right? According to that measure, a random element is normal in every base that's not a power of 3. Okay, so the typical element of the Cantor middle third set is an example of something that is normal in every base that's multiplicatively independent to 3. Okay? And then Schmidt proved an extension of that theorem, a complete analysis of how normality works. So he said, Schmidt's theorem says, suppose you have a subset of the natural numbers greater than the natural numbers that are greater than or equal to 2, namely the possible bases for representations of reals, and suppose it's closed under multiplicative dependence. So if a number is in there, then everything that's multiplicatively dependent with that number is also in there. So if 4 is in there, so is every power of 2, and so on. Then there's a real number xi such that xi is normal for every base in R and not normal for any base that's in the complement of R. Okay, so multiplicative dependence is the defining property that correlates normality between one base and another. Okay, so you can be normal. Normal, recall, means all the words, right, in that base appear with their asymptotic expected value. You can be normal in base 2, not normal in base 3, normal in base 5, not normal in base 6, and so on. You can choose it at will. That's Schmidt's theorem. Oh, by the way, this Wolfgang Schmidt, I mentioned I'm an admirer of Sierpinski. I was curious about him the other night, and I looked it up, and there is something called the Sierpinski Medal in mathematics. And Wolfgang Schmidt was one of the recipients of that medal. Okay, so how does one prove, how do you prove a theorem like this? Well, there is something that remember I said that normality is equivalent to saying that the multiplicative shift, mod 1, is equally distributed. Okay? So there's a way to tell, this is a kind of inverse Monte Carlo criteria, right, which is if you have a sequence is uniformly distributed mod 1, which is a criteria for normality under the multiplicative shift, if and only if you can use the values of that, if and only if for every continuous function on 0, 1, if you use the values, right, as a sample set, right, and take the average value of the function on the sample set, the result converges to the integral. Okay, so uniform distribution means that the sequence can be used to implement the Monte Carlo method to evaluate integrals of continuous functions. Okay, that's Weil's criteria. Okay, so that means now you don't have to look at all continuous functions. You can look at a nice generating set. Like continuous functions have harmonic representations. Right? And so you don't have to look at all f's, you can just look at the harmonic functions. And so xi is normal to base b if and only if the multiplicative shifts by multiplication under b, that's this, right? Correctly identifies the integral of the harmonic functions. Harmonic functions integrate to 0. Okay, so there's an analytic, the short is, there's an analytic criteria to evaluate uniform distributivity, and uniform distributivity is a way to measure normality, and Schmidt's argument was an analytic argument that depended on the estimates of these sorts of sums. Okay. All right. Okay, now, we talked about the arithmetic hierarchy, right, as a way to talk about complexity of definitions of sets. Okay? You can use the arithmetic hierarchy to be a calibration tool. You can look at a set and say, well, how complicated is this set? Right? Well, look at its optimal. It's like saying, how complicated is this set? Well, what's the running time for the optimal algorithm to compute that set? That's a measure of the complexity of the set. Right? In this context, right, you could measure the complexity of a definable set by looking at what's the complexity of its optimal definition. Right? We have this arithmetic hierarchy which has assigned a complexity to syntactic forms of definitions. If I have a set, I can say, what's the best definition of that set? Could I define it by some simpler formula? Right? A good example is, suppose I have a bounded sequence of rational numbers. Okay. I don't want to do bounded. Suppose I just have a sequence of rational numbers. No, bounded is good anyway. I don't care. It can be bounded or not bounded. Okay. To say that sequence has a limit, right, is, you want to say there is an infinite sequence, so that for every epsilon, all the elements, there is a real number, so that for all elements of for every epsilon, there is a point in the sequence after which you're within epsilon of that real number. Okay, so that definition it starts out by saying there is something that you're describing with infinite precision. There is a real number. And these rationals get close, for arbitrary precision, the rationals get to within that precision of the number. But there exists a real something happens. But there's a much simpler criteria for a sequence to be convergent. It has to be a Cauchy sequence. For every epsilon, there exists a point in the sequence after which any pair of elements are within epsilon of each other. That's an arithmetic definition, as opposed to saying there exists a real number such that the sequence behaves nicely with that real number. The elements behave nicely with respect to each other. So that's Cauchy's theorem, and it simplifies the criteria for a sequence as being convergent. Right? It takes it away from saying that there is a real, and it produces to something that's low-level arithmetic. Okay? So the a priori definition of being convergent, right, is not the simplest way to characterize the property. Right? There's a much easier definition to characterize the property of having a limit. Right? It's a sequence being Cauchy. Okay, and a lot of times you prove a theorem. You have some complicated situation, and you prove, well, what's really happening is this. And if the theorem feels good to you, it's because what's really happening is this is a lot simpler than the original description of the situation you were analyzing. You clarified it. And sometimes, often, in logical terms, the clarification is something that is syntactically simpler. Right? Or, it can be conceptually simpler, or it can be syntactically simpler, or it can just reduce it to something that was already known, which is equally complicated, but it was already known. Right? But oftentimes a clarifying theorem goes from a complicated description of something to a much simpler description that describes exactly the same thing. Okay, so you can use this arithmetic definability as a way to calibrate the complexity of sets. What's the syntactic form of the optimal definition? Okay, so now, so A is sigma 0k complete if it's sigma 0k. This is like an NP complete set. It's defined, it's sigma 0k complete means it is sigma 0k definable, and for every other sigma 0k set, there's a computable function so that questions about the arbitrary set can be reduced to questions about the complete set. Okay? So not unfamiliar in the computer science world either. Okay, then, one remark, if a set is sigma 0k complete, it's not, if it's pi 0k complete, it's not sigma 0k. Okay? So unlike the polynomial hierarchy, it's known that the sigma 01 complete sets are not pi 01. The hierarchy doesn't collapse. Okay, so here calibrating the notions of normality. So the first one is that what do we have? If R is a pi 03 collection of possible bases, okay, these are the multiplicative independence generators. If I have a pi 0 property of numbers, there is a real number C, such that C is normal to every base in R and not normal to any of the other elements of the other bases. Okay, so if we have any pi 03 set, right, is the set of bases of some computable number. Okay. So specifying a pi 03 way which basis the number you want to have be the basis for which this number is normal, and you can compute a number that is normal to exactly those bases. So it's consequently, as corollaries, the set of real numbers that are normal to at least one base is a sigma 04 complete set. And so there is something that satisfies the pi 03 property. Well, then, if there is something that satisfies pi 03, the described set R will be non-trivial, and the number will be normal to that witness to the pi 03 property. And if the sigma 04 statement is false, then every number does not belong to the pi 03 property, and the number that's constructed is not normal to any base at all. Okay. And then similarly, in a similar vein, if I have a pi 03 formula, there is a computable number C such that that pi 03 property of C B is true exactly if C is normal to base B. So look at it this way. Take any pi 03 sentence whatsoever. Pick any pi 03 property that you want. Right? There is a computable real number, so that relative, if you look at that pi 03 definition on that number, it coincides with being normal to that number's being normal to base. So the pi 03 property of B relative to the number is equivalent to the number is normal to base B. So normality, if I have a number, right, which bases that number is normal relative to, right, can be coincident with any pi 03 property that could be on which you could evaluate that number. Okay, so normality can be defined by any pi 03 formula whatsoever. Okay, so as I see it, right, the interesting thing about this is if normal to base B can be defined by any pi 03 property, then there's very little else you can say about the property of being normal. Right? It's not different. It's not provably different from any pi 03 property. Right? It's completely uncommitted. Right? Any pi 03 property defines normality relative to some computable real. Okay? So there's nothing special about normality. Right? It can be anything. So that's I find that it's an interesting flexibility in the notion that normality is completely fluid. Any formula whatsoever can define normality relative to some computable real. Okay, now the way that the construction goes is quite similar to, so what do we do? The construction is very similar to the one that I described, right? It goes by recursion on stages. Each stage is defined by a phase. Like previously we had the red phase where we're simply normal for single digits, and then we had a blue phase where we're going to be normal for words of length 2 and so forth. Here it's the same sort of thing, defined by phases, but instead of so we now have this red phase where we're going to be normal to bases B1 and B2 and not normal to base C. Do that for a long time, and then we have to switch, right? We have to switch to normal for B1, B2, and B3, and maybe not normal to C1, and then we switch over to here to, now we're normal to B1, B2, B3, and not to C2, and so forth. And then there's another phase later where it switches again. B1, B2, B3, B4, and C3. And as long as you keep coming back to each of these C's infinitely often, you end up with something that's not normal in base. The things you want non-normality for, you hit them infinitely often below the line. The things you want normality for, you pay attention to them from some point on above the line. And it's a similar sort of, instead of picking out something that's random with regard to Lebesgue measure, right? You pick out something that's random in the fractal so that almost everybody is normal to the B's and it's not normal. So it's something like the Cantor middle third set, except it's the Cantor throw away some digits in base C2, base C3, and be normal for the other bases. So it's a similar sort of construction, but with a different measure each time. Okay. So continuing with this normality theme. The problem of being normal to different bases, being normal to one base and not normal to another, that was the problem that Schmidt solved in the 60s. Now, he was using this analytic machinery, which applied for normality. Its normality is the thing that is equivalent to being uniformly distributed under iterated multiplication. Okay? There isn't, I mean, you could come up with an analytic variant for simple normality, but it's just not that easy to work with. Right? It's not as clean. It would be uniformly distributed for certain intervals and not for others, but it's not as effective to work with. Okay, so I want to turn to the question about simple normality. Okay, so C is simply normal to base B just means, like we said, if and only if every digit appears with limiting frequency 1 over B. Okay, and then there are two theorems about simple normality. The first is if C is simply normal to B to the K times M, then C is simply normal to B to the M. So if a number is simply normal to base 4, it is simply normal to base 2. Right? And why is that? It's because if you look at, as I said before, look at the binary expansions. What do the base 4 digits correspond to in binary? 0, 0, right? 0, 1, 1, 0, 1, 1. Right? If you look at the base 2 digits in those 4 words, they're equally the 0 and the 1, 1 balanced, and the other 2 are internally balanced. So if I have each one of those 4 1/4 of the time, I'm going to have 0 and 1 each 1/2 of the time. So that's this observation. Second observation is a little bit more sophisticated. If there are infinitely many positive integers m such that C is simply normal to base B to the m, then C is simply normal to all powers of B. And that's because for very high power of B, almost every digit in base B to the m is simply normal in base B. So anyway, this is a bit more sophisticated, but it's still sort of naively plausible. Okay, then those conditions which were known necessary conditions on simple normality are exactly sufficient as well. And interestingly enough, this theorem came out of the logical analysis of how normality works. But when you want to figure out what is the optimal definition for some property, you have to completely deconstruct that property. You have to show the property internally is this complicated and no simpler. That means you have to completely disassemble it and see that the ingredients of how that property is satisfied are generic. Every other property of the same complexity can be mimicked by how, like normality. Normality is a pi03 hard property. So any pi03 phenomena can be completely, as we said, completely mimicked and translated into instances of normality. That means you have to completely deconstruct how it is that normality is achieved. When you do that, you have insight into how all the ingredients of that phenomena work and how they fit together. That analysis was exactly what was needed to take Schmidt's theorem and extend it to cover not just normality. Like you have to get if you do something for a power of base 2, you have to do the same thing for all the powers of base 2, right? And so on. They'll break up internally what's happening with normality inside the multiplicative dependence classes. So here's the theorem: a set of natural numbers. M is a set of possible bases, and suppose that these two necessary conditions hold. If k to the m if b to the km is in M, then b to the m is in M. And if infinitely many powers of b are in M, then all the powers of b are in M. This is a property of a subset of natural numbers. That property holds if and only if there is about M, if and only if there is a real number such that for every base b, c is simply normal to base b if and only if b is in M. Okay, so you take any set that has these two properties, there is a number that is normal, simply normal, to exactly the elements of that set. Okay, so it's a complete analysis of how the distribution of digits can work across all bases. And the proof, like I said, of course, it's a number theoretic fact, but a good 25%. I don't know, it's hard to tell. But a good fraction of it is purely the combinatorial ingredients of logic. How do you analyze some situation from the point of view of computability theory and representing the way that formulas are satisfied in the arithmetic hierarchy? And the other part is, well, these are numbers, and you have to know how numbers work, right, in order to get that to implement that combinatorics. Okay, so let me make a couple comments. It's a similar sort of argument that we did before, except instead of building one sequence, you could build a whole tree of sequences. So we could build a whole Cantor-like collection of sequences of the right property. It's the uniform measure. A random element of that Cantor sequence concentrates on reals that do the job. You can make that Cantor, I'm going to come to dimension next time, but you can make the Cantor set as thick as you want. These are not measure 1 properties, because on a set of measure 1, everybody's absolutely normal, and we're denying absolute normality. But you can make the dimension as big as possible. It's a relatively thick set. And it's a fractal, but it's not a self-similar fractal. It's not homogeneous. And as you go up the fractal, the way that it's not self-similar, because we're changing the distribution of the digits as you go up. Okay, but it has the same sketch, and I could to the level of detail that I'm describing things now, it looks like this. There are phases to the construction, and it's the same. It has the same sort of picture that you accumulate a lot of normality before you change your mind on what you're going to do, and then when you change your mind, you're changing base, right? And then there's a little bit of noise when you go from something that is written in, say, a dyadic rational, and you go to something in base 3, you lose a little bit of, you don't have absolute control over the base 2 expansion, right? But the red part is much greater than the noise that's introduced in moving into blue. So that one I thought was an interesting combination of ideas, that normality and then this. So randomness, normality as a characteristic of the random, analyzing the concept, the logical structure of the concept of normality, and then when you do the total deconstruction, you see every little corner of the room, right? Because the whole thing has been laid out. Well, there was a part over there that was still in the dark, right? But we had all the ingredients to see how things were put together. And then you could sort of fill in the number theoretic fact a little bit. So interesting. That was quite an interesting project. Okay, let's see. We are, I think, out of time. Is that right? What time are we supposed to? Oh, we were supposed to end at 5. Is that right? Oh, 5. Oh, okay, good. No, I'm glad. I'm ready. If you're ready, I'm ready. So let's continue. Okay, so we will come back to normality. I'm going to come back to that. So don't completely obliterate it from your memory, but put it to the side for a minute. Okay? Remember how in the beginning, right? I mentioned 2 different conceptual aspects of randomness. One was the Martin-Luft thread, and the other one was the Kolmogorov thread. The Martin-Luft thread was randomness through aspects of measure. Right? A real is random if it avoids really small measure sets. The other that was Martin-Luft. The Kolmogorov concept of randomness was that a sequence is random if all of its initial segments are hard to describe. Right? It's unpredictable. Okay. Now there was the normality you could think of as a Diophantine aspect of the Martin-Luft concept. This irrationality exponent is a Diophantine aspect of the incompressibility concept. Okay, so here's the definition. Oh, and this definition originates with Leoville. Interesting how this came up. Leoville, so you all know how to prove that there is a number that is not algebraic. Algebraic number is a number that's so you could use Cantor's fact, right? So algebraic number means that it's a real number that is the root of a polynomial with integer coefficients, like square root of 2. It's a root of x squared minus 2. Okay, so algebraic number is the root of a polynomial with integer coefficients. There are only countably many such polynomials, and each polynomial has only finite many roots. So there are only countably many algebraic numbers. Cantor's theorem says that the continuum is uncountable, hence there is a transcendental number. That was not the first proof that there are transcendental numbers. The first proof was on the order of 10 years earlier by Leoville. Right? And Leoville proved it using I recommend, right, if you want to see an artful use of elementary calculus, right, look up Leoville's proof that there exists a transcendental number. It's on Wikipedia, so you don't have to look too far to find it. Right? It is a very elegant proof. But the way that he proved it was he showed that algebraic numbers, he invoked this notion of Diophantine approximation. And he showed that, well, let me say what the definition and I'll tell you what Liouville proved. Okay, so for a real number, the irrationality exponent is the least upper bound of the set of exponents z, such that you can approximate, so c is the real number. The irrationality exponent of c is the least upper bound on the set of real numbers z, such that you can approximate c by a rational p over q to within error 1 over q to the z. Okay, so think of what happens if z is 1,000. Right? That says, so I mean, every real number can be arbitrarily well approximated by rationals. Rational numbers are dense in the set of real numbers. However, right, this approximation has to be special. It has to say in the scale of q, right, you can get within c for a lot of qths. Right, so in the base q, if c is a number between 0 and 1, in the base q expansion of c, it will be p and then z many zeros, right? And then whatever is left. Okay, so it's in the scale of q, p qths is a really good approximation to c. Okay, so the irrationality exponent is, well, for how big a z are there infinitely many such q's? Okay, so that's the irrationality exponent. High irrationality exponent means that c is extremely well approximated by rationals. Where extremely well, right, is interpreted, right, relative to, you have to, extremely well meaning look at the fraction, and that's telling you how well the approximation is doing. It's not just that this distance is small, it's this distance is small in terms of, right, the elements of the fraction that described this rational. Okay, so good. High irrationality exponent means it's extremely well approximated by rationals. Okay. Infinitely often, it's easy to describe. Yeah, go ahead.
What is this set of z bounded?
Well, let's see. So, well, I guess here's the theorem is, I guess every real number can be approximated to within 1 over q. P over q is minus the thing is less than 1 over q. So there is a well, I mean, so the least upper bound could be infinity. That's the question. There are numbers that have irrationality exponent infinity. Okay. But they all have irrationality exponent by just crudely, the lower bound is 1. There are numbers that can be well approximated. There's no upper bound, it's just infinity. Infinity is allowed here.
So is this thing easy to understand? Like, for example, what is the irrationality exponent of root 2?
That's a very good question. Okay, so let me get to the next slide. Okay, and then we'll make a couple comments. Okay, so when z is large, you can do very good approximations in this p over q in the scale of q. It's a linear version of Kolmogorov complexity, because Kolmogorov complexity said you could using a short program describe a lot of bits. This is a very short program, and it describes a lot of bits, right? When z is large. Okay, so it's like a metric version of Kolmogorov complexity, where computable is swapped out for rational. So here are the facts. Liouville numbers are those with infinite irrationality exponent. Here's Liouville's example. The sum on n, 1 over 10 to the n factorial. That was Liouville's transcendental number. He showed that all algebraic numbers have finite irrationality exponent. And this number does not. It's well approximated by base 10 rationals. Right? There's a 1, and then there's a lot of zeros, and then there's a 1, then there's really a lot of zeros, and so on. Okay, so that's Liouville's number. Almost every number has irrationality, a random real has irrationality exponent 2. And Roth, in 55, irrational algebraic numbers like the square root of 2 have irrationality exponent equal to 2. And Roth won the Fields Medal for this theorem. That's quite a deep fact. Okay, so irrational numbers, and it's notice like 55, and remember Borel, irrational algebraic numbers are normal. At that time, right, irrational algebraic numbers were seen to exhibit a lot of features of characteristics of randomness. Right, they have this. They are difficult to describe by rationals. For example, so they have the incompressibility features of random numbers. Do they have the normality features of random numbers? Unclear. Okay, so now, randomness, right, just obliterates the irrationality exponent. Right? So there is a natural sort of number theoretic property, right, which Lebesgue measure obliterates. Everybody has the same irrationality exponent. So you could sort of think, as people got interested in how the irrationality exponent works, it's a sort of natural motivation to try to sort of spread out the picture of randomness and see if there is a way. Are some things more non-random than others? If the irrationality exponent is really big, right, that's a little more non-random than if the irrationality exponent is bigger than 2, but not too big. Right? So there's a notion there of a sort of a spread of type.
Why is 2 the sweet spot?
Sorry, say that again?
Why is 2 the sweet spot?
Well, it's the numbers. What can I tell you? So there's the fact that there's an interesting argument that you might have thought that 1 is the sweet spot, but it's because why not? Right? You can always get to within 1 over q by a fraction with denominator q. Maybe 1 is the thing. But it's not. 2 is. And what can I tell you? It's just the way polynomials work. Okay. Okay, so some subsets of the natural numbers are more null than others. Some real numbers are more non-random than others. Dimension, right, is what you use to take that point of being measure 0 and expanding it to inspect its inner structure. Okay, so that ends the discussion on normality, the preliminary discussion on normality and the exponent of irrationality. Okay, so we saw something about the distribution of digits, which has to do with the way we're representing the number, right? And the character of statistical randomness that things are equidistributed. Okay? You can compute, though, you can give absolutely implementable algorithms to produce the base B expansion for any B of numbers that are absolutely normal, but they're not random because they're computable. They're very computable by efficient means. So they are computable but normal. Okay, so normality is a feature of randomness which is kind of orthogonal to being computationally indescribable. Right? You can give a fast algorithm to compute something that, from the point of view of normality, looks random. It's not random, it's computable. Right? But that separates the two notions, right? That the computational description, right, incomputable, random things are not computable. but but being not computable can be separated from being normal. Okay, so now the next thing I want to do is talk about this expansion. Next thing I will do is talk about the expansion of measure to dimension, and then we'll do again, like what's the effect of theory, how is it applicable, and then we'll see how that. Then we'll come back to these concrete examples and see what we can learn about them. Do we have time? Yeah, I guess so. Okay. Maybe what I will do, well, you know what, actually, before I start, this is a whole new topic. Before I start on the new topic, any questions? Yeah, go ahead.
So, the first example of a normal number is computable. This was basically
Yeah, so the Sierpinski-Lebesgue number was not computable. No, it's like I said, what they did is they essentially defined a closed subset of the interval, all of whose elements are normal, and then took the least element. But the least element of a closed set does not, even if you can have a pi01 class, you can have an effectively described closed set which has no computable element. So the Lebesgue and Sierpinski examples are not computable. There's no algorithm, there's just a definition.
So in what sense is it in this logic?
It's a definition in analysis. You know, just a definition, you know. There are sets that are definable that are not computable, like the halting problem. And you can write down a pi0. This is discussing that at the break. There is a pi01 class, an effectively closed set, so that its least element is equal to 1 exactly on elements of the halting problem. All right, so you can write down a computable closed set so that if you try to pick out its least element, you get something non-computable. You can also write down it's a little less tangible. You can also write down an effectively closed set that has no computable element. Any effectively closed set always has an element that is computable from the halting problem, but it's not necessarily computable. Yeah, so those examples, there was no algorithm. There was a kind of from the outside in. It didn't tell you how to build it. It just determined it uniquely. But that was better than just, there exists one because the set has measure 1. Right? There exists this one, which was definite, but not definite by means of an algorithm to compute the digits. Just definite by, it's the unique thing that satisfied some definition. Yeah, like the halting problem. The halting problem that's a perfectly definable thing, but it's not computable.
Do you have any examples of where algebraic non-linear?
No. That's Borel's question. So rational numbers are not normal. Borel's question is Borel conjectured every algebraic irrational number is normal. That conjecture is open. Right, so there are none of them that are known to be normal, and there are none of them to be known to be not normal. Yeah, go ahead.
So it's open in any way, not absolutely normal.
It's open. I don't think that it's known for any irrational algebraic number whether it's normal to any base. So I think that problem is absolutely open, and as far as I know. It's strange, right? It's just that, it's hard that they are different parts of the mathematical realm, right? One is sort of the descriptions by rational approximation, and the other one is very algebraic. And trying to find the path from one to the other is who knows where you're supposed to go. You know, it's
Having computation nowadays are leaning towards.
yeah, all the evidence, the computational evidence is that these things are all normal. But there is I mean, that can be deceptive. Yeah. But I guess the prevailing wisdom is that they're all normal, because they all seem to the rate at which the discrepancy between normality and what you're observing in the algebraic numbers, all the bases are going to zero with the same kind of curve, and everything seems quite uniform and pointing in the direction of normality. And even more so with pi, because pi is one of these things that everybody likes to compute, and so they've computed all sorts of the digits of pi, and it looks normal as well. So so conjecturally all these things look normal. Computational evidence suggests that. But it's open. Other questions? Yeah, go ahead.
So the example of our numbers that we have, do we know that they're not algebraic, or do we not know?
There's I mean, you can make them not algebraic, but there's no sort of hint that they are algebraic. There's nothing to suggest that they would be. Like Champernowne's number. It just doesn't have anything to do with polynomials. Other questions? Yeah, go ahead.
This example of real number, so if we omit some attempts and just take a subsequence of n's, it is still irrational. Yeah. So we make n-computable numbers that have infinite exponents. Yes?
Yeah, like this one. You can get infinitely many. It's once you've got a number like that, where now it is not only is it a Liouville number, it's a Liouville number in that specific base. You're always choosing the denominators to be powers of 10, right? Once it's Liouville, if you take any infinite subsequence of the ones, right, and look at that number in base 10, it's still a Liouville number. Liouville number just says that if it's all base 10, the ones are spread out. The rate of the enumeration function for the ones is a fast-growing function, right? So that's right. Once it's Liouville, if you thin it, it gets even more Liouville. If that makes sense. And like I said, I recommend looking up that proof. It's a half an hour of time well spent to see the proof that Liouville numbers are transcendental. Okay, any other questions? Okay, so I then, in the last minute here, have some questions for you. Let me go back here. Let's go to here. All right, so these first four questions. The first four questions here. All of these questions can be answered using things that we went through today. Okay, so the first one, so I recommend solving all these problems. Right, so the first one is, well, I guess you can read them yourself. The first one, but the first class here is having to do just with effectively presented closed sets. So pi 0, 1 subsets of Cantor space. Okay. So the first one is show that if you have a pi 0, 1 set, it corresponds to the collection of infinite paths through some computable tree. So a tree is just a collection of finite binary sequences, closed, ordered by extension and closed downward. Okay, so you could draw a tree just by drawing some binary thing where the distance between a node and the next split could be, it could have terminal nodes, it could have isolated paths. Every pi 0, 1 subset of the Cantor space is the set of paths through some computable tree. This is an interesting one. If a computable tree has only finitely many paths, all of those paths are computable. If a computable infinite subtree of the sequence, let's do it for one. If I have let's talk through this one. If a computable tree, this is binary, it's a collection of finite binary sequences ordered under extension. Okay, so I have some tree like this. Maybe this goes way up there. Maybe this node is terminal and so forth. There goes the tree. Okay. If that tree has only one path, that path is computable. So suppose the tree is computable. I can compute for each finite binary sequence whether it belongs to the tree. And it has only one path. How do you compute that path? So suppose that it's this tree, right? And
Can you query the tree to ask if some prefix of a path is there in the tree?
you can compute for each finite binary sequence whether it belongs to the tree.
So if you know that it is only one, you can ask all of them in the order. And
So I can't compute. So I know that there's only one path. Okay, how can I tell whether the path starts with a 0 or a 1? Let's suppose that the tree. I'm going to make the tree a little bit better there. There, the tree starts like that. Both the length 1 sequence 0 and the length 1 sequence 1 belong to the tree.
You try both and extend all the sequences.
I want to compute which way does the path go.
You should try both. At some point, like if some particular prefix cannot be extended, you will.
Yeah, so I examine, I go up here and I start computing what's in the tree. Right? And then I compute, this node over here is terminal. Then what do I do?
But you can continue doing like this, and that will be a path.
You can compute. Every time you come to a terminal node, you can say, I better go to the right. Instead of I went left and it terminated, I better go to the right. Okay, but that's computing the path as a limit. I don't want that. I want to compute the path. I don't want to have an algorithm that I don't want to eventually converge to a path. I want to compute a path. Go ahead.
We start in a subtree that all its nodes are terminals, okay, determined in finite time. times.
Correct. Good.
So in parallel means 0 and 1.
Correct.
So time will stop.
Right. The 2 to the omega Cantor, the Cantor set is a closed bounded set. It's compact. If there's no path over here, if this part has no path, right, then it's a closed, empty set. It has an open cover. Right? That cover has to be finite because any open cover of a compact set is finite. That means that if there's no path that goes this way, there's a finite level of the tree at which there's no node. So exactly right. You look at the first branching and you just examine the tree above both sides until you see one of them is finite. And then you know you must go the other way. So the fact that this, if that tree has exactly one path, that path is computable is a reflection of the compactness of the Cantor set. If the tree were infinitely branching, it's possible to have infinite fan-out tree that has only one path, but the path is not computable. But if it's a binary branching tree or a finitely branching tree, where you know the cardinality of the fan-out, if there's exactly one infinite path, then you can compute it. And it's as you said, you look on both possibilities until you see one of them is impossible. And the one that remains is the unique way to go. So that's this one. Okay, then the next one is show that there is a infinite, there is a pi 0, 1 class, there is such a computable tree, such that it has uncountably many paths, right? But none of them are computable. So if it has finitely many paths, they're all computable. It could have lots of paths, but none of them are computable.
So, sorry, the A repeats. So which one?
Yeah, so this one, if it has finitely many paths, they're all computable. It could have a lot of paths, and you can't compute any.
No, I mean that one C, like suppose that A is a subset, and then show that there is a set A.
No, suppose that I have a pi 0, 1 set A such that A is uncountable. A is the pi 0, 1 set, and A is uncountable, but has no, A has two properties. It's pi 0, 1, and it has uncountably many elements.
The problem is probably because at the beginning of the task,
Oh yeah, okay, yeah, right. Yes, right, you're right. You're right, yeah, you're right. Forget about that. I didn't have to say this because it was already set up there. It's an editing inefficiency. Yes, of course, computer science audience is going to find inefficiencies whenever they exist. So, right. So I want an uncountable pi 0, 1 subset of the Cantor set such that it has no computable elements. This is like, there's lots of elements, but you can't find any. Okay, this is half of the Martin-Luff is the same as Kolmogorov notions of randomness. If it's Martin-Luff random, then it's incompressible. And then this one is, try to use that proof sketch, right, to show that, I'm sorry, this should be normal in base 2. Oh, no, I don't have to. It's a subset of 2 to the omega. Right? It's not a real number. Show that the set of binary sequences that are normal, right, is pi 0, 3 complete. And you can use the Champernowne number to be helpful for that one, and use that red and blue device to do it. And then this is an interesting one. If you have a sigma 0 3 set, that's normality is a pi 0, 3 hard problem. If you have a sigma 0 3 property, that's a somehow simpler property than normality. And every normal number has this property. Show that there is a computable real which has the property P. I don't know why another editing error. So S is sigma 0, 3. Every normal number belongs to S. Show that S has a computable element which is not normal. So if I have a sigma 0, 3 property that's true of all normal numbers, it's true of some number that's not normal. Example of a sigma 0, 3 property would be something like, even better, every word occurs at least once. Okay, that's a pi 2 property. For every finite block, there is a place in the sequence where that block appears. Okay, so that in infinite, in this kind of infinite combinatorics of words, that property is called being rich. Okay? So it's show that there is a real that is rich but not normal. A sequence, a binary sequence that's rich but not normal. Okay? That would be an example application. But any sigma 0, 3 property, like the digits 0 and 1 are equally distributed up to epsilon. So there is a point after which the frequency is within epsilon of the expected value. That's a sigma 0, 3 property. And it's rich. Any sigma 0, anything that's simpler than pi 0, 3, you can find a number that is, if the property doesn't contradict normality, you can find a number that has that property but does not have the property of normality. Okay, so those are the problems. Good luck. And then I'll see you tomorrow.